Good afternoon, students. I'm sorry that I'm not here with you today as the freshman retreat is here, but we are still going to be learning new material about rational functions. As you can see on the board to your left, I have a bunch of new definitions, new and old, that you should look at before you start this worksheet. So if you haven't, take a look at the board, pause the video, and look at those definitions. The worksheet I'm asking you to complete today is finding all of the different things that we need to graph a rational function. So to get a complete picture, we're going to need to know if it has any holes. We're going to need to know if it has any x-intercepts, y-intercepts, what are the vertical asymptotes, horizontal asymptotes, and if there are any slant asymptotes. The easiest ones for you guys to find will be the x-intercepts and the y-intercepts because those are not new to you. So let's go ahead and do that first for number 1. By definition, x-intercept is when y is 0. So I'm going to set the whole function equal to 0 as such. We would have 0 equals x minus 1 over x plus 1. Now when I have something equal to a fraction, to simplify that fraction I would multiply by the denominator. So my denominator is x plus 1, so I will multiply both sides of my equation by x plus 1, and in doing so, this side will cancel because I have 1 in the numerator, 1 in the denominator, and on the other side I have 0 times something, which will always be 0, so I get 0 equals x minus 1, which in turn x would equal positive 1. Now the x-intercept is not a line, so I'm not going to write x equal 1, it is a point. So I would write 1 comma 0 because y was 0. Now let's do the y-intercept by definition. That's when we plug in 0 for x. So if I do that, I'll do that over here on the side, we get 0 minus 1 over 0 plus 1, and that would simplify down to negative 1. And again, the y-intercept is not a line, it is a point. So we would have 0, negative 1. Now holes. Holes are where the function simplifies, where we ended up canceling something from the numerator and denominator. Now the function I gave you up there at the top, the original one, x minus 1 over x plus 1, that is its simplified version. We cannot simplify this function any further, so therefore, since nothing cancels from the numerator and denominator, this has no holes. So we will write none in that box. Okay, vertical asymptotes. Those ones are going to be new. Those ones are going to come from what we divide by 0. So if you think back to the parent function, we approached the axes to where we got really, really close to it, but you guys never could actually cross them or touch them, right, when you're drawing your parent functions. So we're going to have that same concept here. What can't you divide by? Well, we can't divide by 0. So in order to find where we would be able to divide by 0, we're going to set the denominator equal to 0. So to find my vertical asymptote, I'm going to take x plus 1 equals 0, and I in turn get x equals negative 1. Now the vertical asymptote is a line, so you guys will just directly write that over here. Horizontal asymptotes, you guys can see that there were 3 rules on the board. Number 1, the exponent in the numerator is greater or less than the exponent in the denominator. So if I look here at my original problem, well, my numerator exponent is 1, my denominator exponent is 1. So one's not greater than or less than the other, they're equal to each other. So if I look back at my rules, where is that true? Well, that's rule number 2. If they're equal to each other, then I'm going to divide the coefficients. Well, what's the coefficient in front of x? That would be 1. The other coefficient in front of x would be 1. So my horizontal asymptote would be equal to 1 divided by 1, which equals 1. And again, we're going to write that as an equation of a line. And if you have a horizontal asymptote, you will not have a slant asymptote. So we will not worry about slant asymptotes here because they do not exist. Okay. Once you have all of your information, now comes the fun part of actually drawing that graph. So we can use our calculator for assistance here as well, okay? But we're also going to sketch what we already know. So let's label our axes. We'll scale by 1. I can see that I have an x-intercept at 1, 0, so I'm going to put a nice heavy dot there. I have a y-intercept at 0, -1, so I'm going to put a nice dot there. And then I have a vertical asymptote at -1, and this is where you guys can use some colors. Asymptotes we're going to indicate with a nice dotted line. It's still going to be straight, going through whatever number it needs to, but it will be a nice dotted line. And the other one happened when y was equal to 1. So y equal to 1 is a nice horizontal line. So I'm going to draw a nice dotted line going this way. And I can see already that I have points in existence down here, which means that I will have points across from that. Just like in the parent function, we had points across from each other because it still has to abide by our function rules, which means that we cannot fail the vertical line test. So these 2 points are going to be my guide, and I'm going to connect them with a nice rounded edge where I get closer and closer to my asymptote, but I'm never actually touching it. And I will use these as a guide on the other way where I'm getting really close to my asymptote, but never actually touching it. Now I don't have any guides up here, so I need to get some help with that. Where I can find those points are with your graphing calculator. Okay? And if you plug this into your graphing calculator, you'll be able to see on the table that at -3, 1, 2, 3, we're going to be at 2. So I'm going to put that point there. And from there, again, I'm going to use the asymptotes as my guideline, and I'm going to draw a nice rounded curve approaching either asymptote. Now I would like you guys to try number 2 and 3 before you watch the next video.